Wanted to work through a problem that involves black body radiation. So black body radiation is electromagnetic radiation. It's a spectrum of electromagnetic radiation that is emitted by all objects, bodies. So you emit black body radiation. I emit black body radiation. The Earth emits black body radiation. The sun emits black body radiation. The intensity of the black body radiation is a strong function of the temperature. It goes as the fourth power of the temperature. The maximum wavelength of the black body radiation, the peak wavelength of the black body radiation, is also a function of the temperature. And in this example, we're going to calculate the peak wavelength of black body radiation that's produced by lightning, which heats up the air, and by a nuclear bomb that heats up the air. And we're going to use the temperatures of the air that's produced by lightning, the temperature of the air that's produced by a nuclear bomb, to calculate the peak wavelength of the black body radiation from the lightning or from the nuclear bomb. We're going to be using what's called the Wien law. So let me start by writing that down. So this is the Wien law. It states that the product of the peak wavelength, the maximum wavelength of the black body radiation, and the temperature of the black body is equal to this constant, 0.0029 meters Kelvin. Now, this is an empirical law, an experimental law, an observed relation between the wavelength and the temperature. It's not an exact, precise theoretical law. As I say, it's empirical, observational, experimental. When we think of this law, you might want to be thinking of the black body radiation spectrum. So to see the black body radiation spectrum, we might plot the wavelength of the black body radiation versus the intensity of the black body radiation. It has a distribution that looks like this. At very long wavelengths, the intensity shrinks, disappears to nothing. At very short wavelengths, the intensity also shrinks, disappears to nothing. The intensity peaks, has a maximum at this maximum wavelength. And so that's what we can calculate in using the Wien law. That's what we can relate to the temperature of the black body in using this Wien law. Anyway, in our case, we're asked to think about two temperatures, one of lightning and one of the nuclear bomb, and calculate the corresponding peak or maximum wavelength. So let's start with the lightning. Rearranging the law, the Wien law, we can write the peak wavelength, the maximum wavelength as 0.029 meters Kelvin divided by the temperature. In this case, that's 0.0029 millimeters Kelvin divided by 10 to the 4 Kelvin. That's the temperature. And I've calculated this. It came out to be 290 nanometers. 290 times 10 to the minus 9 meters. So this is lightning. Let's do the same thing, the same calculation for the case of the nuclear bomb. Again, to calculate the peak wavelength, we're just going to take the value of this constant, 0.0029 meters Kelvin, divide it by the temperature. In this case, that temperature is 10 to the 7 kelvins. I'm dividing by 10 to the 7 Kelvin. That's 10 million Kelvin. And when I make this calculation, I get 0.29 nanometers, 10 to the minus 9 meters. And this is the nuclear bomb case. And so we've calculated the peak wavelengths for these temperatures of black body radiation emitted by the heated air, by the lightning or the bomb. For reference, 290 nanometers. That's a little bit shorter than visible light. This is ultraviolet light. And then this wavelength, 0.29 nanometers, that's much, much shorter than visible light. This is X-rays. And so a lightning strike, well, we see a flash of lightning. That is some of the black body radiation from the lightning strike. But the peak of the black body radiation from the lightning strike is actually ultraviolet light. And well, we've probably not seen a nuclear bomb explosion, but you would see the nuclear bomb as visible light. But the peak of that light is actually a long way from the visible light. It's in the X-ray region of the electromagnetic spectrum. Anyway, this was an example of black body radiation. As I say, all objects, you, I, and everything else emit black body radiation. The amount of black body radiation that you, I, and everything else emit is in strong proportion to the temperature, goes as the fourth power of the temperature. And the peak wavelength is related to the temperature also. So the higher the temperature, the shorter the wavelength. Blue light, blue black body radiation corresponds to a higher temperature than red light. That's a lower black body temperature because blue light is shorter wavelength. Red light is longer wavelength. So blue light would correspond to higher temperature. Red light would correspond to lower temperature.